Hello, these are the solutions in video form for suggested problem set 5.2. So, the first problem has a set of three masses that are hung from three identical springs, and each mass has 8.5 kilograms as its mass, and each spring has a spring constant value of 7.8 kilonewtons per meter. So I'm going to go ahead and convert that to newtons per meter. So that's 7,800 newtons per meter because there are 1,000 newtons per kilonewton. And then each spring was 12.0 centimeters long before any mass was attached to it. So I'll say that x naught is 12 centimeters, which I can go ahead and convert as well to 0.12 meters since my spring constant's in meters. So part A asks us to draw a free body for each mass. So I'm going to go ahead and do that. So we'll go ahead and number these. This will be 1, 2, 3. And I will do these in the same order. So for mass number 1, I have, hopefully I'm in equilibrium after I hang my mass. So I have a spring force going up, so the spring force we'll say is 1, and then I have some weight going down, so I'll say this is the weight of 1, and then I also have a spring force going down as well. So in fact, I know that this is actually going to be longer than my weight because I have two other masses below it. So I'll say that this is Fs2. So I have Fs1 in this spring here, Fs2 in this spring here. So this is for mass 1. For mass number 2, I have going up Fs2, I have weight of 2 going down, and then I have Fs3 pulling me down. Then for mass 3, I have Fs3 pulling up, I have the weight of 3 pulling down, and that's it. There is no spring force pulling down afterward. Now B asks, how long is each spring when it's hanging as shown? And it gives us a hint. It says isolate only the bottom mass and then treat the bottom two masses as a system, then treat all three as one system. So we're going to do exactly that. So we're going to start by looking only at the bottom system. So if I look at the sum of forces in the y direction for only mass 3, what does that look like? Well, I have force in spring 3 going up minus the weight of mass 3 going down is equal to MAY3. Now, I'm assuming we're in equilibrium afterward, so we're going to say the acceleration for this is 0. So the force in spring 3 we can rewrite as K times delta x 3 minus mg. Now they're all the same mass, so I don't need to specify that this is mass 3. And that's equal to 0. So my delta x3 here, if I rearrange this, would be equal to mg over k, which substituting would be 8.5 kilograms times, we'll go ahead and use 10 here, 10 newtons per kilogram, over my 7,800 newtons per meter. So if I plug this into my calculator, I would get 0.0, let's see, we're going to round this a little, 0.0109 meters. Now this is the delta x3, and the question asks for how long each spring is. So since this is my delta, I'm going to have my x naught plus my delta x3, which would be equal to the length of x3, so spring 3. And so that's, actually, let me go ahead and write that as an L, the length of 3. And that's going to be, if I substitute, my 0.12 meters plus my 0.0109, or the length 3 would be equal to 0.1309 meters. And I'm going to leave it like that because it's very small to begin with. So I'm going to go ahead and treat it like that. Now, I'm going to go ahead and move up to mass 2. So what I want to do here is I want to treat all, or I guess both, of these two masses as one system. So I don't care how long this third spring is, I only care how long the second spring is. So I'm basically going to be treating it as two masses put together. So I'm going to have the weight of 2 plus 3 pulling me down instead of Fs3 and W2, and Fs2, the only force pulling up. So if I do that, the sum of forces is quite simple. So the sum of forces at 2 is going to be Fs2 minus the weight of 2 and 3 together, and that's going to be equal to MAY2, which we're just going to say is 0. And so now I have K times delta X2 minus, now 2mg, because I have two masses here, and that's equal to 0. So my delta X2 is going to be 2mg over K. Or it's just going to be 2 times what we had for number 3. So delta X2, without really doing any extra math, it's just going to be that 0.0109 times 2, which I can easily put in my calculator and get 0.0218 meters. So my length for spring 2 is going to be my initial length plus delta X2, which would end up being, if I write this out, 0.12 plus 0.0218. And so the length of spring 2 is going to be 0.1418 meters. Yes, I know I'm not using significant figures. Now, by the same pattern that we're kind of noticing here, since this just involved two of the same mass pulling down, the spring at the top is essentially supporting the weight of 3 masses. So the pattern here would lead me straight to saying, so I'm going to just write pattern, saying that delta X3, oh, I should say that I'm doing this backwards, aren't I? So this should be delta X1, and that will be 3 times my 0.0109, or I could say this is 3 mg over K. And so delta X1 is going to be 0.0109 times 3, which is 0.0327 meters. So the length of spring 1 is going to be that 0.12 plus 0.0327. And so the length of spring 1 is just 0.1527 meters. So the important part to get out of this is that if I have a linked mass system, I can really think of it as different partitions of those masses. So I can think, oh, this top spring is supporting the weight of all 3 masses together. And I don't really care how these forces internally act. I only care about the fact that there's 3m experiencing the force of gravity, and this spring is supporting all of that weight. Question 6.43 is meant to be a very simple application of an alternate definition of work. So we know that a force is applied to a 2 kilogram model car, and it's only applied in the x direction, and here's my x component of force plotted as a function of the x coordinate of the car. So we want to calculate the work done by that force when the car moves from x equals 0 to x equals 3 meters. So the alternate definition that I'm talking about here is that work is the integral of force with respect to distance. So if I'm looking at the work done from x equals 0 to x equals 3, graphically, I know that that work is represented by the area beneath this curve, or the area bounded by the force function and the position axis. So for A, that's going to be this area right here, which should be 1/2 2 times 2, which is this triangular portion, plus my base of 1 times 2. And so this ends up just being, let's see, that's 2 plus 2 is 4, and then that's newtons per meters, or 4 joules. And that's the work done from 0 to 3. B says, what about from 3 to 4? Well, the area here is 0, so the work must be 0. There is no area open there. For C, from 4 to 7, well, that's just this triangular area plus this non-area. And so that would be 1/2 times 2 times -1. So be careful because this force is negative at this point. And so that's going to be -1 joule. So we have negative work for that portion. Then for D, I want the total work across the entire thing. And so that's going to be 4 plus 0 plus -1 joules. And therefore that would be positive 3 joules. It's my net work. And now E kind of messes you up. It says, all right, what happens if I go from 7 meters down to 2 meters? So how exactly does this work? Well, I'm essentially doing an integral in reverse. So I'm actually going backward. And what does that mean for me? Well, if I'm going backward here, I'm actually going to say, for this portion right here, that my area would be 1/2 times now a -2, because I'm moving in a negative direction, so my displacement is negative for that area, times my force of -1, plus, again, a 0, and then I'm going to the 2 meter mark. So now my base is -1 meter times my height of 2 newtons. And so when I go through this, I actually end up with a positive 1 joule here, minus 2 joules for this portion, and my overall work moving backwards is actually -1 joule for this. So the general thing here is that if I'm moving backward, I actually am going to have the opposite sign for that area. So if this was a positive area, if I'm moving left to right, then if I'm going backward, I would say that's negative area, or negative work done. So question 6.46 is kind of an interesting conceptual question, where we have an ideal massless spring that we are cutting in half. Now, if I cut this in half, let's imagine now that I have 2 different springs and I'm supporting the same mass. Now, they're not actually different springs. They're the same spring, but this is K1, and then each of these would be K2. So what is the force constant for each half of this spring compared to this spring here? Well, let's look at the force on these in order to figure out how exactly this works. So if I take this spring and I look at the forces acting on the mass, I would have K1 times X minus mg equals 0. So K1 here is equal to mg over X. Now if I look over here, what spring is actually first acting on this mass? Well, I actually have 2 different springs, so I need to do one at a time. So if I look at this force right here, that would just be K2 times whatever X it does, so we'll say it's X2, minus mg equals 0. Okay, so K2 is going to be equal to mg over X2. Okay, well, that's my first spring. Well, the second spring is going to be almost identical, right? Because if I look at right here, I would have K2 X2 pulling up minus K2 X2 pulling down. Well, that makes sense. But the question is, what's happening with this X2 compared to this X? Well, think about it. I have a smaller spring that has a larger mass pulling down on it. So, what do I need to do? Well, since I have half a spring, I'm going to think about this as half of the displacement. So what does that mean? Well, x2 would be equal to 1/2 x1. Or I could rewrite this as 2 times x2 equals x. I think this makes more sense though, so we're just going to go back to that. Forget I said this. So that means that K2 is actually going to be equal to 2 mg over x. So all I did was I substituted in 1/2 x for x2 and moved that 2 to the top. So that means that when I cut this spring constant in half, or when I cut this spring in half, it actually doubles the spring constant. So does that make sense? Absolutely, because each spring has to support the weight by itself. And since each spring is only half as long, it's only going to be able to stretch half as much. But that means then that the spring constant has to double in order to have that exact same force. So we end up with this weird situation where cutting a spring in half actually doubles the spring constant. So cutting a spring in half doubles its K. Or I can say that K2 is going to be 2 times K. Now B says, what if I cut it into 3 equal segments? What's the force constant on each one in terms of K? Well, by the same token, so this is all part A, if I were to cut it into 3 pieces, well, let's think about what happens here. My sketch would be something like this, where just this bottom spring needs to support all of the weight. And so I would have some situation where each of these is going to be moving, but now only 1/3 the displacement. So my K for 3 cuts is instead going to be 3 mg over x, or 3 times K. So cutting it into thirds is now going to be giving me 3 times the spring constant. Question 6.49 merges calculus with our definitions of work and the work-energy theorem. So we know that work is equal to the integral of force with respect to position. And we know that work will be equal to the change in kinetic energy of an object. So I'm given a forcing function here. F is a function of x. Again, this is a clue if you see f is a function of x that you will need to do some calculus. So what all is going on here? Well, I also know that m is 6 kilograms. So if my box is initially at rest at position 0, what is its speed after it's traveled 14 meters? So let's go ahead and set up this entire thing. So I have the integral of f, which is this function here, so it's 18 minus 0.53x dx, and I'm integrating from 0, which is my initial position, to a final position of 14. This is going to be equal to my delta k, so this is my change in kinetic energy. So I would have 1/2 m times v2 squared minus 1/2 m times v1 squared. Now I'm initially at rest, so this whole term is 0 because v1 is 0, and that just means that I'm solving for v2 in this case. So before I do that, I'm actually going to go ahead and do my integration. So I'm going to integrate this, and so 18 integrates just to 18 dx just integrates to 18x, and then 0.53x or negative 0.53x actually integrates to negative 0.265 x squared. And then we are evaluating this from 0 to 14. And then on this side, I'm going to go ahead and plug in my 6. So I would have 1/2 6 times v2 squared. And so on this side, I'm going to have to use my calculator to do this. So I will have, in case you've forgotten, 18 times 14 minus 0.265 times 14 squared, and then minus, go ahead and write all of it out, 18 times 0 minus 0.265 times 0 squared, just for those who are struggling a little with the calculus, is equal to 3 times v2 squared. So I'm going to go ahead and divide both sides by 3. This whole thing is 0. So I have 18 times 14 minus 0.265 times 14 squared divided by 3. And so right now I have 66.687, we'll round, equals v2 squared. And so solving for v2, we end up with just a final speed of 8.17 meters per second. So this is just a combination of calculus and the work-energy theorem. Question 6.54 is an interesting question because we actually need to use both energy and kinematics in order to figure out how much power is produced by the friction as the rock stops. So I'm going to start with a quick free body diagram. Here's a rock. It's sliding on a surface. It has initial speed of 8 meters per second. We'll say to the right. It has a mass of 20 kilograms, and it has a coefficient of friction of 0.2. So my free body actually ends up being mg pulling down, normal force pulling up, and then a friction force to the left that we don't quite know. So a little bit of work. For the y direction, my force normal minus mg will be equal to may, which is 0. So my normal force in this case is just equal to mg, or I can go ahead and do my math. So mg is going to be 20 kilograms times, we'll go ahead and use 10, so that's 200 newtons. And so my force of friction, so if I look at forces in the x direction, is going to be the only force acting in the x direction. It'll be acting negatively, equals max. And here my acceleration is not 0, so I'm actually going to be looking for this acceleration. And that will tell me that, let's see, so that's going to be negative, let's go ahead and write it out, negative Fn times, do it this way, negative mu times Fn equals max. Ax would just be equal to negative mu Fn over m. So substituting here, I have negative 0.2 times 200 newtons over my mass of 20 kilograms. So my x acceleration is going to be negative 2 meters per second squared. So why do we need this? Well, we need to know how long the rock is accelerating to a stop. So initially, my rock has 8 meters per second as its speed. So its k initial would just be 1/2 mv naught squared, which is 1/2 times 20 times 8 squared. So this kinetic energy, according to our definition of kinetic energy, is the amount of work that would have to be done to this rock in order to stop it. So for this rock, that would be 640 joules of work. So I would need to do 640 joules in order to stop this. So the question is, how long does it take for that to occur? Well, I can say then that because I'm accelerating at negative 2 meters per second squared, and my rock will start at some velocity and go to 0, that the time that it takes, so this would be 0 equals 8 minus 2t, will be 4 seconds in order for it to stop. So power is going to be the work that I need to do to this over the time that it takes to do that work. So for me, that is going to be negative 640 joules over 4 seconds. So the power that is produced by this friction, now I guess in this case it doesn't really matter if it's negative or not, will be 160 joules per second or 160 watts. So I could say that it's negative if I wanted to. Technically it is negative because friction is pulling energy out of the rock. It all depends really on how the question's phrased. I would accept either for this question. But be careful because we have another definition of power, that is power equals F dot V. Now this is only at a constant velocity. Here my rock is stopping, so it's not actually at a constant velocity. So be careful and don't just use that blindly because you see a velocity and you can find a force of friction. All right, so for question 6.62, we have a bulky cow. So for those of you who have never seen this word before, if you balk at something, that just means you resist at doing that. So the cow is resisting you pushing her into the barn. And the coordinates with the origin at the barn door have the barn door at the origin, and the cow goes from 0 to 6.9. And you apply a force with the x component Fx, given as this function. How much work does the force you apply do on the cow during this displacement? So I'm going to use my definition of work as the integral of force dx. And here I'm going to rewrite that as the integral from 0 to 6.9, which are my beginning and ending coordinates, of negative 20 plus 3x dx. So because of the properties of integrals, I can pull this negative sign out. So I have negative integral 0 6.9, 20 plus 3x dx, and now I can go ahead and integrate. So I have negative, integrating 20 becomes 20x, integrating 3x becomes 1.5x squared, and I'm evaluating from 0 to 6.9. So this is going to be a little odd, but we'll go ahead and do it. So we have negative of 20 times 6.9 plus 1.5 times 6.9 squared minus, I'm going to go ahead and write it all out, 20 times 0 plus 1.5 times 0 squared, close bracket. And so this whole set is 0 because every term includes a 0, and I'm evaluating at a 0 location. On this left-hand side, I have 20 times 6.9 plus 1.5 times 6.9 squared. And this gives me 209, but don't forget there's a negative that I would need to distribute. So this is going to be negative 209, I'll say 0.4, joules, and that is the work that I have done to this cow. So something that's interesting here is that my work is actually a negative force while my displacement is in the positive direction. So it seems that my work is actually, all it's doing is resisting the cow moving out. So this is kind of a weird situation, but it makes sense that my work here is negative because I'm trying to pull energy out of this unruly cow. For question 6.70, we finally get our first non-ideal spring. So it says that this spring does not obey Hooke's law. One end of the spring is fixed, so we have a fixed end over here, and then here's our spring. And then in order to stretch or compress it by an amount x, a force along the x-axis with this component given here as a function of x must be applied to the free end. So I'm going to go ahead and rewrite this with my values for the constants. So that's going to be kx. I don't know why it's not a, but this is our life now. So that's going to be 100x minus 700x squared plus 12,000x cubed. And so please note that when x is greater than 0, the spring is stretched. So this is my positive x direction. So how much work must be done to stretch it by 0.05 meters? So that means that I want to know the work done for x going from 0, so this is my 0, to a positive 0.05 meters. So that work must be done is going to be equal to the integral from 0 to positive 0.05 of my forcing function, which is 100x minus 700x squared plus 12,000x cubed with respect to x. So this is going to be a quick polynomial integration. So that's going to be 100. I'll just do it one easy step at a time. So 100x squared over 2. Go ahead and add brackets. Minus 700x cubed over 3 plus 12,000x to the fourth over 4, evaluated from 0 to 0.05. So all of these terms have an x in it, so I'm not going to worry about the zeros so much. So that means that my work is going to be 50 times 0.05 squared minus 700 thirds times 0.05 cubed plus, let's see, that's going to be 3,000 times 0.05 to the fourth. So the work done here, I'm going to pause for a second and do my calculator work, will be a whopping 0.115 joules. I know, it's a huge amount. Fantastic for all of that work. So now this is to stretch the spring by 0.05. So let's see what happens when we compress the spring by 0.05. So what's different? Well, instead of integrating from 0 to positive 0.05, I'm going to integrate from 0 to negative 0.05. So it's the same setup with a different set of bounds for my integral. So it's going to be 0 to negative 0.05, and that's integrating 100x minus 700x squared plus 12,000x cubed with respect to x. So hopefully you did the first integral correctly, which means you can just set it up the exact same way, although you're substituting negative 0.05 instead of positive 0.05. So what does that do for us? Well, we have 50 times negative 0.05 squared minus 700 thirds times negative 0.05 cubed, interesting, plus 3,000 times negative 0.05 to the fourth. So my work here will be, again positive, but 0.173 joules. So C asks us, is it easier to stretch or compress the spring? Well, looking at the amount of work that we need to do in order to stretch versus compress, it appears that it requires less work to stretch it. So stretching this spring is easier because there's less work. So why, in terms of the dependence of fx on x, is this true? Well, we have this negative term in the middle that whenever we compress it, actually becomes positive. So first off, in order to understand what's going on here, we have to do positive work to either stretch or compress this spring. That makes sense. We need to put energy into this spring in order to store energy in the spring, no matter what. But because of this negative term, when we actually go through and calculate the work done, we end up with any compression that is negative, so any compression, so my x is negative, is going to end up with a positive middle term. So the work here will always be larger than the work done to stretch the spring. So that's really just going to be the reason that this boils down to be true, because of that x cubed term after integration. So that's really why we end up with a positive or a more positive amount of work for any time that we compress this spring. So question 6.71 is in parentheses because it is a cumulative problem and it is rather difficult, especially if you haven't looked at circular motion in a while. So we have a block of mass 0.06 kilograms attached to a cord that is passing through this hole on a frictionless surface. The block is originally revolving at a distance of 0.4 meters from the hole with a speed of 0.7 meters per second. So I'm going to go ahead and draw this up. So I have a block on a string, it's going in a circle, and it has a radius of 0.4 meters, and it is going at a speed of, we'll say v1, of 0.7 meters per second. And then some stuff happens. So A asks us originally, what is the tension in the cord? So in order to figure that out, I'm going to do a sum of forces. So here I'm just going to do sum of forces centripetally because that's what I'm looking at. And that means that I don't need to worry about the weight or the normal force. I only care about this centripetal force, which is in fact tension. So I only have the tension pulling inward. And so that's going to be a tension, which is equal to MAC, or MV1 squared over R. So this tension is going to be the mass, which is given to be 0.06 kilograms, times V1 squared, which is 0.7 squared, over my radius of 0.4 meters. So plugging all this in, I find that the tension will be a huge 0.0735 newtons. So that is the tension originally. Now B says, what is the tension in the final situation when the block has a speed of 2.8 meters per second? So the difference here is that I have a smaller radius. So my new radius is 0.1 meters, and my new velocity, still traveling in a circle, is 2.8 meters per second. So again, I have a new tension, so I'll say this is T1, and then this is T2. And so my sum of forces centripetally is going to be now T2 equal to MAC, or MV2 squared over R. I guess this is R1 and this is R2. And so my new tension is just going to be 0.06 times my new speed of 2.8 squared over my new radius of 0.1. So my new tension is going to be a much larger 4.704 newtons. Now here's the fun part. C says, how much work was done by the person who pulled the cord? So in order to figure out how much work was done by the person, I'm going to look at the change in kinetic energy of my block. So work is equal to the change in kinetic energy, which would be 1/2 mv2 squared minus 1/2 mv1 squared. So let's see. That work is going to be 1/2 times 0.06 times, now I'm going to do 2.8 squared minus 0.7 squared. So I'm lumping this together and factoring out the 1/2 m. So according to this, my work would be 0.2205 joules. Which is kind of weird to think about because we said that a force could not, or a force that is perpendicular to motion could not do any work. Well, in this case, the only way that I can increase the speed of my block is by doing work to the block somehow. So that work comes out in the change in kinetic energy of the block, So even though this tension force is perpendicular to the motion of the block, it is doing work by increasing the speed of the block.